I have a vector B. Let's say this is A and this is B, and then this vector is C, which is equal to A plus B. This relation, or this plus this is equal to this, is independent of coordinate system. Right? You don't have to write, or any coordinate system that you write, you choose, the components of this will be equal to sum of the components of these two in any coordinate system. Even the independently components may be different. But these relations among the vectors have the character of coordinate system independence. Correct? If I choose a coordinate system like this, x, y, then A vector may be written in this as Ax into Ex. Ex is the unit vector along Ex direction plus Ay Eu. But if I choose another coordinate system like this, from x prime y prime, then same A may be written as Ax prime, Ex prime, this way, Ay prime, Ey prime, where Ex prime, Ex prime are the unit vectors along x prime and y prime. So components will change. Components of the vector will be different in different coordinate systems. Whereas the relation like this, if you write x prime y prime, Cx prime will be same as Ax prime plus Bx prime. Cx is same as Ax plus Bx. So this relation is independent of. So there are some rules, some laws, some relations that do not depend on the choice of coordinate system. This we know as a vector. When we write a vector in this symbol, when I write a vector in this symbol, this object is coordinate independent. I don't know what the coordinate system is, but this is the vector. I can draw a line, geometrically I can draw a line. An arrow like this is a coordinate independent description of the vector. Choice of coordinate system further helps us in understanding components, resolving the vector in terms of components. And that component structure depends on the coordinate system. Okay, this is very primitive, simple understanding of vectors. Now we can actually generalize. So this is a vector on a plane. So I have two components. I can have a vector in the space. I have three components. Now I can generalize this and then say I can have a vector of arbitrary number of components. I can have 4 components, 5 components. This is a generalization. But you may not be able to visualize that space geometrically. Is a limitation. But nevertheless, mathematics does not restrict you in any way to make this generalization. So you can actually generalize, depending on the number of components, you can actually generalize the vector to higher and higher components. 4-dimensional vector, 4-component vector, n component vector, in fact infinitely many components you can have. Just like this A is an abstract notation of a vector with no reference to coordinate system, we can also think of an abstract notation of a vector with having no reference to coordinate system in any arbitrary dimension. Okay, we can actually continue this itself, but this arrow in our mind represents an arrow like this. This arrow is a geometrical arrow. So beyond 3 dimensions, such a geometry cannot be visualized. But the moment I put an arrow, in my mind change the notation and then have some other object to represent such a coordinate frame independent description of an abstract vector. Okay, so sometimes I was thinking that if I write an arrow like this, a vector k, okay, usually this is not how the arrow is written, but just for fun, let me write the arrow like this, because sometimes we have to have a base for shooting an arrow. And if I write it like this, and then erase the arrow, that means I am erasing the geometry, and then slide it into this. This becomes a Dirac-Sket. In fact, Dirac-Sket is actually an abstract representation of an arbitrary vector without any reference to coordinate system. This continuous transformation of a classical vector to Dirac's vector is what I am doing, so it's not standard, so please do not think that this is a very standard way to do it. So by erasing that geometrical arrow and then putting this there is what I cooked up, but essentially what I mean to communicate here is that Dirac-Sket is exactly like this arrow. This arrow does not have any reference to coordinate system. Dirac-Sket also does not have any reference to coordinate system. So when I say coordinate system here, we have to generalize that notion also, which I will do it in due course of time. But what this arrow geometrically represents, this Sket represents in the absence of geometry. Okay, so even though it is introduced in the language of quantum mechanics, it is not restricted to quantum mechanics at all. It is a notation, that's all. You can use it anywhere you like. Okay, so this is our Ket introduced by Dirac. So whenever you want to do any subject, quantum mechanics, classical mechanics, statistical mechanics, you don't want to have any reference to coordinate system, you can resort to this notation. So this is more abstract, general notation. Having said that, I can also have another representation. Suppose if I choose a basis, or if I choose a coordinate system, then the components of the vector are known. Once coordinate system is chosen, you can write the components. So since I can say that the vector A can be written as the column matrix of its components, A is A, Y. No loss of generality. This is just another way of representing. You can write it as, so I have written A is equal to AX into BX plus AY into EY. This was one way of writing. This is another way of writing. A is defined as column matrix. Now what will be this vector EX? From these two, you can immediately write this vector EX is also a column matrix, and that column matrix turns out to be 1, 0. Every vector will be written as a column matrix. The vector EY will become a column matrix given by 0. Now AX and AY are scalars. AX times this vector plus AY times this vector will give you this. So in terms of column matrix representation, you can have these things given a coordinate system. In the same way, you can write down any arbitrary Ket A as a column matrix. A1, A2, whatever is the number, doesn't matter. It's a higher dimension, higher number of components are large, it can be principal infinity. So you can have a ket vector which is exactly like this. This notation is parallel to this notation. If you choose a coordinate system, you can write always the column matrix of components. So if you understand that ket vector is a column matrix, you wouldn't make any mistake in using it. So ket vector is a column matrix if you choose a coordinate system. If you don't choose a coordinate system, ket vector is a ket vector, it's an abstract vector. Just like A plus B equal to C can be written without knowing coordinate system, there can be some relations among ket vectors which you can write without bothering about coordinate system. So if you want to do quantum mechanics without any reference to what coordinate system you want to choose, you do it in the ket vector language, and final result you realize in any representation that you want. You use this coordinate system, then finally you express it. But entire quantum mechanics can be done without choosing any coordinate system. So that is the advantage of choosing this abstract notation. Okay. So anyway, we will talk about it more as we go along. I thought it's very simple to understand, that's why I introduced in the first 10 minutes.